So in this video, we're mainly going to be looking at collisions, and we will apply this to two different problems, one of which is an inelastic collision, and then a very similar collision but elastic, and we'll talk about what that means. But collisions are very common in real life, and so we have car accidents or a plane accident. We have collisions happening in sports all the time. Whether it be between a ball and a foot or just between two people. We also have the idea of molecular collisions, and so the collision theory of reactions, for example. In order for things to react with each other, they must collide, and so we have this idea of a chemical reaction as well with collisions on the molecular level. So collisions are all over the place, and it's nice to learn more about them. So moving forward, basically a collision is an instance of one moving system striking against another. And so we have this idea of momentum coming back in, and impulse, which is any sort of change in momentum. And remember the momentum conservation that we have, so whatever the momentum is before the collision has to be equal to the momentum after the collision. And then we can look at the energy. And so now that we know the energy principle and the momentum principle, we're going to kind of combine both of those together and look at the energy and momentum during a collision. And we can start to classify different types of collisions. And so we'll just go through one collision real quick as an example. Before the collision, you're going to have some sort of initial velocity. And let's say there's two different objects colliding. And so you have the initial velocity of the first and initial velocity of the second. After the collision, you're going to have the final velocity of the first and the final velocity of the second. And so for an example, we have a car colliding here with a different car, which initially is at rest. And afterwards, they are both going to be moving. Now, the first car here, car A, is twice as massive. And so we'll take a look at what's going on. What we're going to do with a lot of these collision problems is we'll set the momentum before equal to the momentum after, and we don't even necessarily need to look at the energy. And so we'll take a look at this and we'll say, okay, well, the momentum of car A before plus the momentum of car B before has got to equal to whatever the total momentum is after. And you start to break that up, and momentum is mass times velocity plus mass times velocity and so on. And we get zero momentum initially for B, and we have 1,000 for A. And notice how afterwards it also is going to be 1,000, but it's going to be 200 coming from A instead of 1,000. And then the majority of the momentum after the collision is coming from car B with 800. So that's kind of how it works, right? The total momentum before equals the total momentum after. In this case, it's 1,000, but the way that you get to 1,000 can change. And so instead of 1,000 plus 0, it could be 200 plus 800. That's the idea of conservation. We can also look at this with energy too. A special type of collision in which the energy is conserved as well is elastic. And so then we have momentum and energy conservation. But in other cases, we will have either a superelastic if we gain energy, like with an explosion. So we have some sort of, let's say we have zero movement beforehand, and then something explodes, and then you have some energy. So masses will start at rest, let's say. It could be called a superelastic collision. We can also have inelastic or even perfectly inelastic collisions, which are much more common. And in those cases, energy is going to be lost. And so we can think about that being lost due to heat or whatever, but the energy is not conserved. And if it's perfectly inelastic, the maximum amount of kinetic energy loss, that's going to be a situation in which the masses stick together after the collision. So the final velocity of the first and the second mass are going to be the same. And so this chart kind of helps a little bit classify the different types of collisions based on momentum and energy. And the other nice thing is we have some equations here for an elastic collision, because during the special case in which you have both momentum and energy conservation, we can derive some new equations that will help us. And so if you're wondering where these equations come from right here to look at the final velocities after the collision, we will show you right now. So for elastic collisions, what we'll do is we look at the momentum and we'll say, okay, well, for a collision, momentum is going to be conserved. Let's assume that here. And so we get an equation 1 that represents this idea of momentum being conserved. And then we have energy is also being conserved. And so we can derive this equation 2 that represents the energy being conserved. And then we can look at the momentum and the energy together. And so we'll plug in equation 1 into equation 2. And so we will arrive at this nice new equation 3 here. And so we have kind of 3 different equations that we have to describe elastic collisions. These aren't as useful to us, and so we'll kind of just do some rearranging here, and we will get some useful equations. And so for the final velocity of the first mass, we're going to solve equation 3 for the final velocity of that of v2f, and then we'll plug it in. We'll basically eliminate that. So we'll solve for v2f, and then we'll plug it in, and we'll solve for v1f. And when you go through that algebra, you get that equation there. And then the same type of thing over here for the final velocity 2. We'll solve equation 3 for v1f, and then we'll plug it in to kind of eliminate that. And then we'll end up solving for v2f. So we have these 2 equations that result from momentum and energy both being conserved, which only happens with a elastic collision. Okay, so now you kind of know where those equations come from. So let's apply this to 2 different problems. The first one being this problem where we have a mass at rest, and we are going to be colliding with a different mass down here of 2m. And then at rest, we're looking at what sort of height are we going to get. The collision doesn't happen until we get to the bottom, so we're only looking at the collision right at the bottom, and so we have some stuff happening before the collision, and we have some stuff happening after the collision, and we also have that stuff happening during the collision. And so we kind of break it up into 3 phases as we're looking at this. But the general idea is we are going to be looking at the momentum principle and the conservation of momentum, and we'll be looking also at the energy principle. And so we are going to assume that the speeds are much, much less than the speed of light. We can get rid of error resistance as usual, and we're looking at the system being the block, the clay, and the earth. And so this piece of putty or clay or whatever at the bottom is that 2m, and this is the block. And so the surroundings we can just basically say is the track. And then step 1, what we'll do is we'll use the energy principle to figure out what's going on before the collision, and then we can use the conservation of momentum to find what's going on during that collision and just after. And then we can use the energy principle again to figure out what's going on when the speed becomes 0 for that maximum height. That's the general idea of how we're going to solve this problem. So if you recall, because they're sticking together, if you remember from before, this will be an inelastic, specifically a perfectly inelastic collision in which they stick together at the end and they have the same final velocity. Like after the collision, they are going to travel together and their masses will combine. And so that's the maximum amount of kinetic energy loss for that collision. And so what we'll do is we're looking at this perfectly inelastic collision, and we will then use step 1, and we'll say, okay, well, the initial position is up here at h. and then the velocity right before it hits we can solve for, because we know we have some gravitational potential energy up here, and we have kinetic energy 1/2 mv squared down here, and so we can set mgh equal to 1/2 mv squared, and the velocity at the bottom is the square root of 2gh right before the collision. And step 2, we'll look at the collision itself, and we'll say from that momentum principle, we have this idea that the momentum before is equal to the momentum after the collision. And so once you set, okay, well, what's the momentum before? Well, you have this mass, m, moving at velocity, which we just solved for, and the 2m is at rest. That's what's happening before. And then after, they're going to combine to be, 3m, and it'll be moving at a certain velocity after. And so once you set up that equation here, we can get an expression for the final velocity of both, and that'll be a third. So the final velocity is 1/3 the v that we solved for here. And what we'll do then is, now we have this new velocity here at the bottom. It's going to keep moving. It's going to lose kinetic energy and gain potential now. And so we have a new amount of kinetic energy, and it's being converted into potential. So we have a new 1/2 mv squared at the bottom being converted into mgh here, which is not going to be as high as it was before, which makes sense. If it was a perfect situation and there was no collision and nothing like that, then it would eventually get back up to its no friction. It would eventually get back up to h, but it's not going to quite get there. And this is also not drawn to scale. But once we do that algebra there from the energy conservation, we will get the final height of h over 9. And so 1/9 of this here. So that's the idea of problem 1 here, where we have maximum amount of kinetic energy loss. We're dealing with a perfectly inelastic collision. So for problem 2, it's a very similar situation. In this case, though, we are colliding elastically. They are not sticking together. And the cool thing is we do have the energy and the momentum conservation during that collision because it's elastic. And it even says collides elastically. A lot of times they will say that just to so that you know. And so what are we going to use? Well, we're going to use the energy principle and the momentum principle. And we're going to look, in this case, that because they're not sticking together, we actually want to know what are the heights, plural, of each block. So they're both going to continue moving up the ramp, but they're going to probably get to different heights. And so we have 2 different heights that we're solving for this time. And we're going to assume that we're traveling much, much less than the speed of light. The dimensions of the blocks are negligible compared to the height. We're basically treating them as point particles. And the collision is head-on. It's a nice perfect collision at the bottom. So we are definitely, in other words, if this were to collide at like a downward angle, that would not be as perfect here. We're going to assume that it's perfectly happening here at the bottom. Everything is spaced amazingly. And we have the system being the blocks in the earth and the surroundings being the track. We are going to use the energy principle, similar to the last one, to figure out what the speed is right before it hits. And then we'll use the momentum and energy principle together to take a look at what's going on during that collision. And then we'll use the energy principle separately for each block, because we're going to have 2 different final velocities to figure out the 2 different heights. So that'll be the strategy. So what we'll do, we'll look at what we had for an elastic collision. Remember, we had those 2 formulas. I showed you where they came from earlier, how to derive them. It comes from the idea that momentum and energy are both being conserved. So we can kind of use these equations, which is nice. And so we'll look at the energy principle first, though. And same as the last problem, it's a very common result. mgh at the top equals 1/2 mv squared at the bottom. We solve for v. The velocity at the bottom is a square root of 2gh. And so that's the speed right before the collision. So now we know an initial speed of both, because this one's at rest and the other one is moving at square root of 2gh. And we'll figure out what's going on after. So we'll use these two equations here. And we can kind of simplify it, though, because we know the initial velocity of the second mass is 0. And so you can kind of see how these equations are going to simplify a little bit. But we're basically using these equations here. And when we plug in for m2, we can use 2m, and it kind of simplifies down. And we are going to get a final velocity of the first object here of 1/3 of square root 2gh, and then the final velocity after that collision of the second mass here of 2/3 square root of 2gh. And now what we'll do is, because they're traveling at different speeds after the collision, they're going to get to different heights because they have different amounts of kinetic energy now after that collision. And so we will go to step 3 and we'll say, okay, well, block 1 is going to have this amount of speed, so we can look at, we'll plug that in for the kinetic energy, and we'll say, okay, well, the kinetic energy at the bottom here that it has after that collision is going to be equal to the gravitational potential at the top, and we will solve for the height for that first one, which will be h/9, which is similar to the last problem, and the height of the second object will be 4/9 h. And so notice how we have the first object here moving with less velocity. It's not going to get as high. It's only going to be 1/9 of h. And then the second object is 2/3 of the square root 2gh, so it's moving faster. And that is going to get all the way to 4/9 of h. And so that's how we take a look at this problem too. Hopefully that illustrates nicely how we can look at collisions, and we can kind of combine the energy principle with the momentum principle, and we can start to classify different types of collisions based on momentum and energy conservation. And we saw 2 examples here, one of which we had energy being conserved and the other one we did not. And we will continue to move forward, and we'll take a look at the next principle, which is the angular momentum principle. And so we will see you in the next video.